Hello there, welcome to your guide on the carbon cycle and energy security for the Edexcel A-level. So in this video, we're going to cover EQ1 of carbon and energy, and that is how does the carbon cycle operate to maintain planetary health. So we're going to look at the link between carbon and the fluxes, stores and transitions of carbon in the atmosphere and on land and in the oceans, and the relation of that to the planet and planetary health. So just a reminder that you've got a booklet that goes along with this video that you can use as a revision guide to go through and to fill in. And finally, that this doesn't replace the lessons you've had in school. This is very simply just to support your revision and to build on your previous knowledge. So we're going to start with the carbon cycle then and what it actually is. So the carbon cycle shows the transfer of carbon through the terrestrial landscape systems, the ocean and the atmosphere stores as well. You can see the image on the right hand side here, shows you all of those different aspects within the carbon cycle. And of course, the main component in the carbon cycle is CO2, carbon. It's not just a natural cycle in the sense that we as humans have an impact on it from vehicle and factory emissions and from our general everyday activities as well, and anything that uses energy. As well as that, there are other natural features of the carbon cycle, like animals and plants in any environment, which have an impact on the amount of CO2 that is going into and coming out of the atmosphere and oceans as well. So the fluxes between each of the elements on the landscape vary and are measured in two ways, either petagrams or PG and gigatons or GT. And so they are just the units of measurement we use to measure the amount of carbon on the fluxes between the different stores. Now, to give you an example of how important carbon stores are, on the left-hand side at the bottom there, we've got a number of stores, including sedimentary rocks and ocean sediments, oceans, fossil fuels, soil and peat, atmosphere, and land plants. And you can see the billion tons of which they store carbon. And of course, you can see there then that sedimentary rocks and ocean sediments are by far the largest carbon store. You can also see that oceans are a significant sized store as well, with the smallest store there being land plants. And even though that is at only 560 billion tons, that's still a significant store in terms of the balance it creates between the atmosphere, the oceans, and the soil that the plants are planted in. So we're going to start looking at geological carbon now. And geological carbon is referring to geology, which is rocks. Now, most carbon, as you've just seen, is stored in rocks, carbonate rock, mainly found in limestone in the ocean. But there's also shale and clay and some other rock types which are created biologically, which store carbon as well. Now, sedimentary rocks are formed in low energy environments. So you can link that back to low energy coastlines from your coasts topic, where layers are deposited and built up over time. Compression then compresses those layers together and creates chemical reactions in the sediment, creating the carbon itself. So carbon is essentially created in these rocks by chemical reaction and compression. Now, limestone, as I've just mentioned, is formed in oceans. And the Himalayas mountain range is one of the largest carbon stores in the world. Now, this relates to oceans because the Himalayas started out life as an ocean-rich sediment, which have been unfolded over time due to plate tectonics. And carbon contained in that Himalayan rock has been eroded and weathered over time, and therefore has been transported back into the oceans via rivers. So you can see that cycle taking place within these limestone rocks in the Himalayas, formed in oceans millions of years ago, and that limestone weathering and transferring that carbon back to the oceans. So that is a cycle. We've also got shale, coal, clay, and other forms of rock, and these are made up to 300 million years ago from the remains of organisms, and organism remains decay and compress, just like any other type of limestone rock. And the subsequent burning of these rocks, so for example, burning of coal, releases that CO2 or carbon back into the atmosphere. And we need to think briefly about geological processes here. So what processes are involved in the geological makeup of rock and how that links to carbon dioxide. So geological carbon can also be released into the atmosphere through geological processes. One of those is where carbon dioxide in the atmosphere reacts with moisture, and that forms carbonic acid. That acid then falls onto the surfaces of rock and slowly dissolves them. This is basically chemical weathering, and it decomposes the rock over time. And that's one of the ways in which we can have geological carbon take place. Another process is that carbon dioxide already exists in the Earth's crust, and volcanic eruptions and outgassing, the release of gas from a volcanic eruption, can release gas into the atmosphere, and that adds to further the amount of carbon being released into the atmosphere. Now, one of the important aspects of EQ1 of this topic is to look at ocean sequestration. So oceans are really, really important as a carbon store. They are the Earth's second largest carbon store, and they store up to 50 times more carbon than the atmosphere itself. And we have what's called a biological pump in the ocean. Now, all this simply means is the transfer or flux movement of carbon dioxide. Now, the carbon dioxide moves to the ocean surface through photoplankton and also photosynthesis. And they are converted back into carbon dioxide food for zooplankton as well. Most of the carbon at the surface of the ocean is recycled. Some of it obviously evaporates into the atmosphere, but 30% of it sinks into deep water before being converted back into carbon dioxide store. So biological pumps is all about the flexibility or flux in movement of the carbon to the surface of the ocean, and some of it then, 30%, sinks back down deep into deep ocean water, which is converted back into a store of carbon dioxide. And we also have physical pumps, and this basically moves carbon compounds to different parts of the ocean in downwelling and upwelling currents. So we know that the ocean has these downwelling and upwelling currents, and that is all controlled by temperature and wave movement. Downwelling currents bring dissolved carbon dioxide to the deep ocean floor. Eventually, those deep ocean currents and downwelling currents form part of what's called the thermohaline circulation process. And then some of that carbon dioxide is released back into the atmosphere as well. Now, remember, just briefly, the thermohaline circulation process is the global system of surface and deep ocean currents driven by temperature and salt quantity and between different parts of the ocean. It's like a giant conveyor belt around the world of where warm and cold ocean currents lie and where the general circulation process of the ocean is. And that plays a really huge role in carbon stores on the carbon cycle, because that is impacting where the carbon moves, where it evaporates, and so on. We also have the idea of terrestrial sequestration. Now, process is similar, except for terrestrial means land-based. So this is the storing, flux, and transfer of carbon from land-based sources. You can see the image on the right-hand side here that's been annotated for you is showing you the process of how carbon moves through a land system with a tree. So we know that trees naturally store carbon. They take in carbon dioxide, and eventually that transfers into soil as well below the tree. We know that fallen leaves and branches also add carbon to the soil, as do dead plants and animals. We also then know that carbon is lost in the atmosphere from the tree and soil due to respiration. That goes into the atmosphere then, but some of that comes back through photosynthesis to help the tree obviously grow, and that maintains the carbon cycle. So plants sequester carbon out of the atmosphere through photosynthesis. As I've said before, plants need photosynthesis to grow and survive, and carbon is actually stored in the plant through photosynthesis. Animals that eat plant matter store it as carbon, fat, and protein, and respiration returns that carbon in those animals back into the atmosphere as well. Also, animals, remember, decompose, and so do leaves, into the soil, and that stores the carbon into the soil. And remember that the food chain means carbon becomes part of the animals, and when they die, the carbon is released back into the soil. So the food chain works hand in hand with the water cycle and the carbon cycle in this case to create that carbon cycle balance. Now, there are two timescales of carbon movement here that we're really referring to. So this is just two key things to remember in relation to timescales. The first timescale can be diurnally. Now, that means during the day, the fluxes are positive back to the atmosphere. So there is more carbon going back to the atmosphere than there is coming back to landscape. But the reverse then applies overnight because photosynthesis is not taking place. And there is also the timescale of seasonally as well, where during winter, carbon concentrations are lower because there's lower plant growth and less photosynthesis. But during spring and summer, concentrations of carbon rise because photosynthesis is occurring at a faster rate. Now we have the idea of biological carbon. So on land, soil is the largest store of carbon. Soil is extremely important in storing carbon. Dead organic matter stores carbon for centuries before it breaks down and is taken up by plants, and then released by respiration and photosynthesis into the atmosphere. So soil, as I said, is the second largest store of carbon. That means it's really important to maintain soil health, and it's really important for plant growth as well. The amount of carbon stored in soil depends on climate, vegetation cover, soil type, and land use. Now, the reason for this is because that all of these different elements, which are varying elements, impact the amount of carbon that's actually available to transfer into the soil. We know that, for example, the more plants there are in a soil and the more rich in nutrients soil is, the more carbon it's likely to have. And also land use impacts it because if we clear landscape and if we deforest for urbanization, for example, building a town or a city, that will decrease dramatically the amount of carbon in the soil and will also disrupt the natural carbon cycle and the water cycle as well. We also have to consider, when looking at planetary health for EQ1, the greenhouse effect and how the natural greenhouse effect actually takes place and the balance between carbon because of this natural greenhouse effect. So the greenhouse effect is really, really important in regulating the Earth's temperature and precipitation amounts. Earth's climate is driven by what's called shortwave radiation. So 30% of radiation is reflected back into space, and nearly 70% is absorbed by the Earth's surface and oceans. Now, what we're essentially saying here, therefore, is that the greenhouse effect is really, really vital in terms of photosynthesis, but also vital in terms of how much heat the Earth naturally receives and how much carbon is therefore being transferred between the atmosphere and terrestrial stores and oceanic stores and so on. So the radiation that's reflected back into space is a natural process and is needed. And the radiation that is absorbed by the Earth's surface is also needed because that also contributes to the amount of carbon we can have in the system. Now, you will also be aware that there is the enhanced greenhouse effect, which is the human impacts on the greenhouse effect. Now, we will dig into that a bit later in this topic, but essentially, the greenhouse effect itself is natural. We don't really impact it as humans. It needs to happen. The anthropogenic or the enhanced greenhouse effect is where we add more greenhouse gases, more carbon into the atmosphere, and that is the damaging aspect of carbon relating to climate change. Now, on that then, we need to make sure that we try and maintain a balanced carbon cycle. And what I mean by a balanced carbon cycle is where all of the different components in the carbon cycle work harmoniously together. There is a balance and even split of where carbon is stored as much as possible. There is the same amount leaving as coming into a certain store. Now, this isn't always the case, and greenhouse gases, human uses of greenhouse gases, has put a significant dent in the balance on the carbon cycle. Now, photosynthesis, that process involving plant growth from the energy transfer from the sun to the plant, is really important in the balance of the carbon cycle. It keeps carbon dioxide levels constant and maintains the Earth's temperature at a stable rate. But photosynthesis varies spatially. It varies in where it is at highest and lowest rates, and that's due to climate. The idea of NPP, or net primary productivity, is essentially the amount of matter available to humans and animals to harvest or consume. So net primary productivity and photosynthesis is highest in areas that are warm and wet around the world. So the key type of area or region being a tropical rainforest biome, whereby there is constant warm temperatures throughout the year. There is high levels of precipitation. So the amount of organic matter or product being produced is high. Soil health is also really very, very important to maintaining a balanced carbon cycle. Now, soil health depends on the amount of organic carbon actually stored in the soil, and that then is determined by inputs like plant and animal remains, nutrients, and also what comes out of the soil, like decomposition, erosion rates, uptake of animals and plants for growth, etc. So what I'm saying here is that soil health depends dramatically on the amount of carbon that is stored in the soil. And carbon gives moisture retention capacity to soil, and this means that the soil is able to keep its health and keep the ecosystem productive. So, for example, the amount of carbon stored in a tropical rainforest area is usually quite high in the soil, and that helps the soil maintain its moisture retention capacity, its ability to be able to hold lots of moisture. If you strip out carbon from the soil, you will find that the soil is no longer have the high ability it had to be able to store lots of water or moisture and have a high capacity, and its health will decline. Now, onto human interactions, if you like, in terms of fossil fuels and our combustion of fossil fuels. So, us burning fossil fuels has implications for our climate. We know that it means that there are rising greenhouse gases in the atmosphere, and that leads to rising global temperatures. It does mean that there will be more precipitation and evaporation taking place at a higher rate as well. It means that the patterns we have of weather, temperature, and climate in general are shifting. We are seeing more extreme events of drought and rainfall, and we are seeing also more variation in climate between different regions than ever before. But it also has implications for ecosystems. So, for example, sea levels rising due to ice sheets and glaciers melting is affecting the ecosystems of coastal areas. Coastal cities, people are all under threat as a result of sea level rising. And remember, sea level rising is a direct result of global warming, and that is a direct result of fossil fuel combustion. But ecosystems in general are seeing a decline in the amount of goods and services they provide, and good quality goods and services and products for us as humans. They're also seeing a decline in biodiversity and changes in species distribution, as well as that relating to our oceans, because the oceans are also seeing a threat due to changes in ocean surface temperature and so on. And finally, there is obvious implications for the water cycle or the hydrological cycle. Increased temperatures and evaporation rates, as mentioned earlier, mean more moisture to circulate around the cycle, and that can create more instability in the cycle, which can lead to changes in our climate as well. So that is a brief roundup of all of the main things in EQ1. The next GeogPod will be on EQ2, looking at the consequences of our increasing demand for energy around the world. Hopefully you found this useful, and I'll see you in the next one.